So last time we talked about the Nernst equation of the general reaction, but today we're gonna focus on the effects of the associated chemical equilibrium on the electrode potential. So what does it mean? So let's consider this one. So we know that or we can open the standard electrode potential table as well, that the silver plus silver electrode potential is plus 7.799 volt, and this is its half reaction. And yeah, this is the half reaction. If you open, if you are interested in the standard electrode potential of the silver chloride silver, so silver chloride silver, and you can open the standard electrode potential table, and you will find that this reaction has the half reaction potential of 0.222 volt for this one. And maybe another reaction that you are interested in is the complexation, like the thiosulfate reduction to be silver solid. So the second one is sodium chloride reduction to be silver. And this one will be silver thiosulfate, which is complex. Is reduced to be silver. And you open the standard electrode potential and you get this number. But it turns out that you can start from the basic one, the most basic one. So this one, you can start from this one and use it to derive the standard electrode potential of these two reactions. You can do that because you can see that silver plus has the oxidation number of +1. Silver has the oxidation number of 0. So for the second reaction, silver chloride silver has the oxidation number of +1 too. And the product is also silver solid, so the oxidation number is 0. So they are in the same oxidation state. For the third reaction here, silver thiosulfate, the oxidation number of the silver is also +1. And the product is also the silver solid. So all these three reactions has the same oxidation state or oxidation number for silver in the reactant and in the product. So the Nernst equation of these three reactions is kind of related to each other. So that's why we can derive the Nernst equation of we can derive the standard electrode potential of the second and third reaction from the first one. So what do you need to do is you need to write the Nernst equation of this reaction, and you substitute the appropriate form or appropriate terms with the solubility equilibrium constant Ksp, or the complexation equilibrium, which is Kf, right? You learn from Ajahn Monpisha, Kf or beta. And this may be sounds a little bit too complicated, but let's do this together. So for this one, I leave some white space so that you can take the note. So I'm gonna show you how to calculate the standard potential of silver chloride silver. So this one, right? Silver chloride silver from the silver ion silver. So I'm gonna show you this, how you can start from this and you show this one. So first, you have to write the standard electrode, you have to write the Nernst equation of this reaction. Silver plus electron, and you get silver solid, because we want to start from this one. So this equation has the Nernst equation of E equal to E naught of the silver plus silver minus, let's do the 25 degrees Celsius from 0.0592 over 1, right? Because this is one electron process, so the denominator is 1. And the logarithm of 1 over silver plus, because silver solid, we don't include it in the equilibrium expression, so you need only silver plus. Now, we want to start from this and to get the standard electrode potential of silver chloride silver. And what you have to do is that, let's do this. So we want to substitute we want to change this term. We want to change the term in the logarithm. So how we can do this? We're gonna use the solubility product constant. So we are doing the silver chloride. So let's write the equation for this one. So silver chloride solubility gonna get the silver ion plus chloride ion. When the silver chloride dissolves, it gives you the silver ion and chloride ion. So what is the standard? What is the KSP for this one? It is the solubility equilibrium. So you have KSP. So the KSP of this one is what? What is it? What is the KSP of the silver chloride? The expression of the KSP.
The concentration of silver ion.
Silver ion
Multiplied by the concentration of
multiplied by chloride ion. Good. Okay. So we know this. The KSP is equal to silver ion concentration by the chloride concentration. What we have to do is that we have to substitute this term, the 1 over silver term, by this term. So we have KSP, this one. So we're just gonna have to rearrange. Oops, sorry. We have to rearrange this one. So we need 1 over silver. So let's do this. So 1 over silver ion is equal to what? So this one you move it to be denominator. This one you move it to the denominator as well. So this is gonna be 1 over silver equal to chloride over KSP. So this is what you have to substitute in this expression. So you just rearrange this one. This is like a normal algebra. So let's do this. I'm gonna move to the next page. Okay. So this one, so what do you have? You have, let me copy that again. So E equal to E naught minus 0.0592 over 1 log 1 over silver. And then you substitute 1 over silver by chloride over KSP. So let's write that. So it's gonna be this one, 0.0592 over N log chloride over KSP. But now we know the KSP of silver chloride. KSP of silver chloride is 1.82 by 10 to the minus 10. So you can substitute this into this one. You can substitute that. So it's gonna be, and you can substitute this as well because this is the standard electrode potential of silver plus silver. So from the table, this number is gonna be what? 0.799, right? From the table. And the rest is gonna be 0.0592 over 1 log chloride. Let's leave it like that. And KSP is this number, 1.82, 10 to the minus 10. And you can use your calculator to rearrange this. I will let you do it at your home. So turns out you will get this number is equal to 0.222 minus log chloride. So this is the expression for the silver chloride plus electron, and you get silver plus chloride. But what do we want? We want the standard electrode potential of this reaction. We want the E naught. So you have to use the definition, right? So the definition of the standard electrode potential is everything is 1, right? 1 molar or 1 ATM or something like that. And consider this term, you see that we need to substitute chloride. And standard electrode potential, we need to substitute chloride with 1 molar. So it's gonna be E is equal to 0.222 minus log 1. And for mathematics, you know, log 1 is 0. So this term is cancelled. So turns out you get E naught equal to 0.222 volt for this reaction, which is now silver chloride silver. And if you go back, if we go back to the previous slide, then yeah, you can see that the number is the same, 0.222 volt. So this is how we convert from the standard electrode potential of the basic from the silver ion to the silver chloride, which is the solubility equilibrium of the first reaction. So is there any reaction for that? Any question? Yeah, for those of you who just come later, you can go back to watch the recording, and that's fine. So this may be this. I think this is actually the hardest portion of the whole part, whole of my part. The rest is gonna be conceptual, but this one is too much calculation. Yeah, but you need to know, you need to master the nonce equation. So to practice this again, let's do the two examples, the example of 1.6 and 1.7. So, all right, can I move on? So let's do 1.6. So the example 1.6 is similar. So we want to show that the silver thiosulfate complex reduction, standard reduction potential or standard electrode potential is equal to plus 0.017 volt. So we're gonna do the similar things. So first we need the equilibrium constant of the relevant chemical equilibrium reaction. So in this case, this is the complex, right? This is the complex. So you need to write the complex station equilibrium constant. Complex station equilibrium constant of this one, silver thiosulfate. And the reaction is gonna be silver plus 2 thiosulfate, because you have 2 here, and you get this complex. And everything is aqueous, so you don't need to put A here or something like that. So the complex station equilibrium constant, or the beta, or actually beta 2. What is beta 2 of this one? So it's gonna be this one, right? So silver thiosulfate complex over silver multiplied by thiosulfate square, because this is 2, so you need 2 here as well. And then because this comes from the same equilibrium comes from the same half reaction as this one, so we're gonna need to substitute this one again, the 1 over silver. So let me copy that again. So from E equal to E naught minus 0.0592 over 1 log 1 over silver. So we need to substitute the 1 over silver term. So how to do this? So you need to rearrange this, right? So it's gonna be beta 2 multiplied by thiosulfate square over silver thiosulfate equal to 1 over silver. So you need to substitute this into this one. And what I didn't give you is the beta value of this one. The beta value of this one is 1.6 multiplied by 10 to the 13, right? Yeah, this one. So let's substitute everything. So this is gonna be 0.799 minus 0.0592 over 1 log beta 2 thiosulfate square over silver thiosulfate. and then you substitute the beta. Let me change my pen. Let's do green. This one has beta, so you substitute beta here to here. All right. So what will you get? You will get something like E is equal to point 0.07 minus 0.0592 log. I will let you do the algebra at home. That shouldn't be like too hard. So you will get this Nernst equation of this one. But again, we want to find the standard electrode potential. So every concentration should be 1. So this is going to be 1, right? And this is going to be 1. And you know log of 1 is 0. So you know that E of this reaction is equal to 0.017 volt, which is the same as what we want to show here. Any question? So if no question, you can come back to go watch the lecture, the language. You didn't change the language. If you watch the lecture and you can you explain how to get the beta 2 again, please? That's from Ajahn Monpisha, right? Ajahn Monpisha lecture. So beta 2 is basically the K equilibrium. Oops, sorry. The beta 2 is the equilibrium of constant of this one. Beta 2 is basically the KEQ of this one, right? The beta 2. It is basically the chemical equilibrium of this one. But now how to make the substitute? Okay, so the beta 2 of this reaction is this term, right? Silver thiosulfate over silver and thiosulfate square. So you need to substitute 1 over silver, right? Because this is the Nernst equation of the one that we are starting from. So you need to rearrange this to get 1 over silver. So this is the algebra. You have silver as in the denominator. So all you have to do is move everything else to the left. So thiosulfate here is the denominator. So you move it as the numerator here with its square. Silver thiosulfate here is the numerator here. So you move to the left, it has to be the denominator. And you substitute this expression in this 1 over silver. So you get this. Same thing, right? And you just substitute later, you just substitute the beta 2 with this one. I didn't give you in the hand now. I think this is the reference value 1.6 multiplied by 10 to the 13. You substitute the beta 2. So you get, and then you may take the beta 2 out, and then you will get this equation. And you substitute the concentration with 1 because we need to find we are finding the standard electrode potential. So this is how you come up with this number. I can show you maybe one more line here, right? So that's going to be 0.799 minus 0.0592 log 1.6 10 to the 13, and then minus 0.0592 log thiosulfate square over silver thiosulfate. Yep. So this term combined will get 0.017, right? Okay, so we have a lot to cover, so I'm just gonna have to move to the next example. This is on the same concept, but this is kind of backward. So if I construct this cell, which is She on the left, And then on the right, you have silver cyanide. And then you have cyanide as well, and silver solid electrode. This cell gives you the cell potential of minus 0.381 volt. Then calculate the complexation equilibrium, the Kf of this silver cyanide. So you're gonna have to start from this one, right? So this is the cell potential, so you need to start from the cell potential. So E cell is equal to E right minus E left. But since E left is what? Is She, right? Standard hydrogen electrode. So it is 0. So we know that the E right is equal to minus 0.381 volt. Then what else? We need to do the same thing again because this is still on the silver thing. So we just write the Nernst equation of silver plus electron, and you get silver. This is gonna be E is equal to standard this one silver minus 0.0592 over 1 log 1 over silver. And our job now is you substitute this, you just substitute everything. E here is basically E, right? So the E right here is minus 0.381. So yeah, minus 0.381. This number is from the table. So the standard electrode potential of silver is 0.799 volt. And you leave 1 over silver, right? That's because you're gonna do that, you do something about that later. So basically, this is the complexation equilibrium of this one, right? Silver, this complex. So now what you have to do is you solve for the silver concentration, silver ion concentration. So I'm just gonna give you the number. The silver ion concentration here is 1.2 multiplied by 10 minus 20 molar. And now, how will you find the Kf? The Kf of this complex. So you need to write the reaction of this one first. So for the silver cyanide, it's gonna be silver plus, and you need 2 cyanide ions. 2 cyanide equal silver cyanide. This one. And the Kf of this reaction is basically also beta 2, but sometimes we call beta 2, sometimes we call Kf. That's kind of the same thing. The Kf of this one is the equilibrium constant of this reaction. So it is silver cyanide. Sorry for the inorganic thing. Silver cyanide over silver and cyanide square. And seems like we know everything. Silver cyanide here is given here, 7.5 millimolar. Silver ion, we just solve for that, it's this one, 1.2 thing. And cyanide is 0.025. So you just substitute everything. So 7.5 millimolar is 0.00750. And silver is what? 1.2 10 to the minus 20. And cyanide is 0.0250 square, and you just plug in your calculator. So do we get 1.0 multiplied by 10 to the 21st as your answer? This one. So this is kind of flipped wave from the previous example, but the concept is the same. I think these 2 examples is the most difficult one from my whole part. The rest is gonna be easier, I promise. Any question for this one? So these examples why do we care about this? Because you can see that it turns out, let me go back to this one. It turns out that, for example, if you think you prepare the silver electrode with only silver nitrate or with only silver ion and silver solid, you're gonna get the electrode potential of this number. But if your system has other chemical species, if your system has other chemical species that can give you other reaction like solubility equilibrium or complexation equilibrium, then it will change your electrode potential that you can read. So to summarize, if you have associated chemical equilibria, it will affect your electrode potential. That's the main idea. And sometimes we know all the reaction, so we can write or derive something like this. But most of the time we don't really know. So what electrochemists use is we use something called formal potential instead. We use something called formal potential instead. So what is it? So formal potential is the electrode potential when the concentration of the relevant species is 1 molar under a specified condition. This is different from the last one. The last one, we know the standard electrode potential. We know that everything has to be 1 molar and it cannot have something else. For example, if we write something like iron 3 plus electron and you get iron 2 plus, that's the standard electrode potential by definition. It must have the anion, but the anion must not have any reaction with this iron. But if you use something as the medium, like if you prepare perchlorate or hydrochloric acid or sulfuric acid or phosphoric acid as the solvent for this reaction, then it will give you some complexation equilibrium or maybe solubility equilibrium, but we cannot write all of the equilibrium. So we just use it empirically by just measuring everything which is in the 1 molar, the relevant species in 1 molar, which is in this case is iron 3 plus and iron 2 is are 1 molar, and measure its electrode potential. And this number is going to be formal potential. We denote the formal potential by this prime symbol. So it's going to be E naught prime for the formal potential. And the reason to use this because we cannot specify all the equilibrium. For example, this one, iron 3 and iron 2, if it's in perchloric acid, it's going to be 0.73 volt. If it's in hydrochloric, it is 0.7. If it's in sulfuric, it's going to be 0.68. And if it's phosphoric, it's going to be 0.46 because iron can have the reaction with phosphate ion, for example. And the standard electrode potential table will give you this as well. And if the problem or if the condition are specified, then you can just use a formal potential instead of standard electrode potential to get more accurate information.